Welcome back. So let's look at limits of composite functions. So limits of a composite function can be found by finding the limits of the individual terms. Let b and c be real numbers, let n be a positive integer, and let f and g be functions with the following limits. The limit of f of x as x approaches c is L, and the limit of g of x as x approaches c is k. All right, so if we have a function and it's multiplied by some scalar, right, that's just a real number. We're just multiplying our limit by some number. So for instance, here would be an example. So f of x is equal to x squared, right? And b was equal to 4. So the limit of 4x squared as x approaches any value we want, c. I'm going to get rid of that box. I really can't stand those boxes. I made another box. There we go. Right? That would be the same as 4 times the limit of x squared as x approaches c. They'd be exactly the same. Right? So a scalar, the limit of a constant, a function multiplied by a constant, is the same thing as the value of the limit times the constant. Right? So the limit of a function times the constant equals the same thing as the value of the limit times the constant. Right? So I could pull that 4 out. And you might think, why would we want to do that? There'll be times when that would be helpful. Right? Not most of the time, but some of the time. Sum or difference. Right? So the limit of f of x plus or minus g of x as x approaches c is equal to L plus or minus k. So in other words, the limit of a sum or difference is equal to the sum or difference of the limits. So for instance, if I had the limit as x approaches c of 5x plus 2, that would be the same as the limit as x approaches c of 5x plus, oh, I'm running out of space. I'll just kind of squeeze it in here. The limit as x approaches c of 2. Right? So the limit of a sum is the exact same thing as the sum of the limits. Product. Right? So if I have the limit of a product, that's the same as the product of the limits. Right? So for instance, if I had the limit of 6e to the x as x approaches c, that would be the same as the limit of 6 as x approaches c times the limit as x approaches c of e to the x. And in this case, I could have, here let me do a different example, because that 6 is a scalar multiple. I could have just factored that scalar multiple out. Let me not do it as a scalar. All right, so the limit as x approaches c of x e to the x. All right, so that would be equal to the limit of x as x approaches c plus the limit of e to the x as x approaches c. All right, so individually, oops, not plus. That's not x plus e of x. Thinking of the last example. Times the limit of e to the x as x approaches c. All right, so since I have a product, I can take the limit of the product or the product of the limits. I can do the same thing if it was a quotient. So if I had the limit, I should use the same example, x approaches c of x divided by e to the x, all right, that would be equal to the limit as x approaches c of x, whatever that is, divided by the limit as x approaches c of e to the x, provided that, in this case, well, we don't have to worry because e of x is never 0, so it's no big deal, right? So here we don't have to worry because the limit of e to the x is never 0. That's always going to be a positive number, right? So, but the limit of a quotient is the same as the quotient of the limits, right? And so here we have the limit of a function raised to a power as x approaches c is the same thing as the limit raised to the power, right? So if I had the limit of x squared plus 3 to the 8th power as x approaches c, right? That'd be the same as the limit of x squared plus 3 as x approaches c, all raised to the 8th power. So I can just find the limit, plug c in, and then just raise the whole thing to the 8th power. Right, so just gives you another way of breaking them down, and they work out exactly the same. Right, so and I just use some real examples just to kind of make sense of our rules. Right, so here's some properties of limits. They come in handy, even more so, when we know what the value of the limit is, right, and we want to do something with that. Right, as you'll see in the next example what I mean. And these things are in your notes. So here we have, and that when you see an R like that, it's supposed to stand for right arrow, and it just didn't work out correctly. So the limit of f of x as x approaches 3, it's supposed to be that, is equal to 7. The limit of g of x as x approaches 3 is equal to 12. All right, so here now we know the values of the limits, so we can use those limit properties to find the limit of the difference, the quotient, or raised to a power, right? And so when we do these, we're going to write them out, right? So the limit of f of x minus g of x as x approaches 3 is equal to, so you always want to write the limit statement, right? Don't just give answers on these, right? It is expected that you write the statement. So the limit of f of x as x approaches 3 plus, and so include this in your notes, the limit of g of x as x approaches 3. And so now that we've rewritten our limit statement, now we can use our properties. So we would have 7, which is the limit of f of x as x approaches 3, minus 12, which is the limit of g of x as x approaches 3. And so together our answer would be negative 5. Moving down, right? So the limit of, as x approaches 3, f of x times g of x is going to be the limit of f of x as x approaches 3 times the limit of g of x as x approaches 3. And so that's going to be equal to, now we can do the substitution, 7 times 12, so that's going to be 84. And then one more example, all right? So the limit of g of x to the 1/2 power as x approaches 3 is equal to the limit of g of x as x approaches 3, all raised to the 1/2 power. All right, so that's going to be, now we can do the substitution. That's going to be the square root of 12, which we should probably simplify. So that's equal to, come on, 2 square roots of 3. Right, because 12 is 4 times 3. And there we go. All right, so there we're using some properties of limits. We'll be using properties of limits all throughout our study of limits. All right, so evaluating limits. All right, so this just kind of shows you how you can think of it. I'm not saying that you have to break it into 3 different limits, right? And then write each of them down. You don't have to do this. But this is essentially why we can just substitute into 5x squared minus 3x plus 2. Right? So it's a limit of a sum or difference. Right? We have a continuous function at 4, so we can find the limit using direct substitution. Right? So long as your function is continuous at whatever x is approaching, at c there, then you can use direct substitution. Right? And let's actually write that in our notes somewhere. All right? So, and instead of, let's put at x equals c. So now I can use this for anything. All right, so in your notes somewhere, if a function is continuous at x equals c, we can find the limit using direct substitution. All right, and that's because, let me change this so it applies to any function. The limit of f of x as x approaches c is going to equal f of c for a continuous function. So add that to your notes somewhere. Just cram it in. Right? So here we have a limit of a sum or difference. Right? We can use our limit properties. So the limit of, I mean, if you really want to get technical, I can make that 5 times the limit of x squared as x approaches 4, and minus 3 times the limit of 3x as x approaches 4, plus the limit of 2. All right, we don't have to break it down like this, but I'm showing you how we're applying the properties, right? So that broken down one, where we broke it down to the limit of each term, is the same thing as the limit of the whole function, right? And so we can just plug into the whole function since they're the same. All right, so that's equal to 5 times 4 squared minus 3 times 4 plus 2. And so if we're simplifying it out so you can see where 70 came from, 5 times 16 minus 12 plus 2, so that's 80 minus 12 plus 2, or 70. All right, so when your function's continuous at some value, you can use direct substitution, which makes it nice and easy. All right, so limit laws. All right, so all polynomials are continuous. You can always use direct, and this one's in your notes, use direct substitution. All right, so add what's over there in your notes, and now let's evaluate. So now my limit is going to be equal to, I'm going to put an equals here. So you do need to write the limit statement. We already have it in our notes, and I have it right up there. All right, so let's call that good, and then equals. All right, so we have 3 times, and now show the substitution. What other simplifying you do after that is one thing, but make sure you show the substitution. Right, because we're showing a property. All right, so 3 times 2 cubed minus 4 times 2 squared plus 11 times 2 minus 5. All right, so that's going to be 2 cubed is 8 times 3 is 24. 2 squared is 4 times 4 is 16. And then plus 22 minus 5. So that's going to be 24 minus 16 is a negative 8, is 8. And then 8 plus 22 is 30, and 30 minus 5 is 25. So here, that's our limit that of the function as x is approaching 2, and it also happens to be the value of the function. Let's look at the second example there and add that to your notes. I didn't give you a lot of room, but you can use a sticky note or something. So for a rational function, factor if possible. Sometimes when you factor, you find something cancels out, and then you can use direct substitution. You can also just try direct substitution if it doesn't look like it's going to factor. Right? I mean, I've got a cubic function, and it's 1/2 as its coefficient. That's not looking factorable because it's cubic. It's not quartic. Can't use substitution here. So I could factor an x out of 2x squared minus x, but it's not going to cancel because x isn't a factor. And I seriously would doubt that 2x minus 1 is going to be a factor of that. All right, so, and if you're not sure and you plug in and you get something that's undefined, well, then you can, and makes no sense, like 0 over 0, well, then you can always go back and say, oops, I should have factored. So for the rational function, factor if possible, and try direct substitution. If you get a real number, no zeros in the denominator, right, the result is the limit. All right, so we have the limit of 2x squared minus x over divided by 0.5. 1/2 x cubed minus x squared plus 1 as x approaches 2 is going to be equal to, so we're not going to write that limit statement again because it's already there. All right, so if it's already there and you can put equals, it's fine. Otherwise, write the question, or write the limit statement. And then show the direct substitution. So we have 2 times 2 squared minus 2 divided by, I'm going to make that 1/2. 1/2 2 cubed minus 2, oops, why did I put that? Although 2 times 2 is the same, I needed to write 2 squared. 2 squared plus 1. So in the numerator, 2 squared is 4, times 2 is 8, and 8 minus 2 is 6. In the denominator, 2 cubed is 8, and half of 8 is 4. And then 4, well, 2 squared is 4, so I've got 4 minus 4, so that's gone, plus 1. Right? Everyone see that? So that's going to be equal to 6. Right? And so here, these are continuous at our value of c, so we were able to use direct substitution. It's that easy to use direct substitution. It's a plug and chug. So polynomial and rational functions. If we have a polynomial function, so if f of x is equal to, so that's just showing you a polynomial function. We've got some coefficient, right? And then we've got x raised to some power, right? And then the exponent, and then we've got another coefficient, and x is going to be reducing in power, right? So if you've got any polynomial function, then you can use direct substitution, right? So you can, as x approaches c, you can substitute c to find the limit anytime it's a polynomial function because they're very well behaved. They're such good little functions. They're continuous everywhere. If f and x and g of x are polynomials and c is any real number, then you can again use direct substitution. So the limit of the function is going to be equal to the value of the function, provided that the value of the denominator does not equal 0. So the direct substitution property is valid for all polynomial and rational functions with non-zero denominators. So long as your denominator is not 0, you can use direct substitution. Right, so we want to find the limit of a rational function. We want to find the limit of x squared plus x plus 2 divided by x plus 1. I'm not going to worry about factoring because first of all, x squared plus x plus 2 is not factorable. And second of all, if I plug in 1, it's no problem because my denominator is not going to be 0. All right, so, and since we have it written, we won't write the limit statement again, is equal to, and now we'll do the substitution. So 1 squared plus 1 plus 2 divided by 1 plus 1. So that's going to give us 4 in the numerator divided by 2, so that's going to be 2. That's our limit. And it's also the value of our function. Right? So here the limit of f of x as x approaches 1 is equal to f of 1 because it's well behaved, it's continuous at that particular point. All right, so here we want to find the limit of x squared minus 4x plus 1 as x approaches negative 2. I'm going to write that because it's really small there. So the limit of x squared minus 4x plus 1 as x approaches negative 2 is polynomial. All right, so we know that's continuous everywhere, so I'm just going to plug in. Negative 2 squared minus 4 times negative 2 plus 1. That's going to be, actually I'll write down here. That's going to be 4 plus 8 plus 1, so that's going to be equal to 13. Let's look at the second one there. All right, so now that does factor the numerator. That would be, I could factor out a 2 and it would be an x minus 3, but notice it's not going to cancel with anything in the denominator. There we go. And also, if I plug in negative 2, it's no problem because it's not 0. Now, if it were as x approaches 2, right, then I'd have to do something about that because that would be a problem. All right, so we have the limit. And actually, we'd have a different kind of limit. So the limit of 2x minus 6 divided by x minus 2 as x approaches negative 2 would be equal to 2 times negative 2 minus 6 divided by negative 2 minus 2. So that's going to be negative 4 minus 6. That's going to be negative 10. And then the denominator, I'm going to have a negative 4, and I need to reduce that to 5 halves. And that's the limit as x approaches negative 2, right? Because the value of the function and the limit of the function are exactly the same. All right, so properties of limits, and I think it's a little out of sequence, but this is at the top of one of your pages in your notes. It's fine in my lesson here. I think it's out of sequence in your notes. Let n be a positive integer. So the following limit is valid for all c if n is odd. Right? So, and it's valid for c greater than 0 if n is even. Right? So the limit of any radical as x approaches c is just equal to, we can just substitute because radical functions are also continuous. Right? So long as we're defined, so long as it's not an endpoint, right? And it's defined. Right? So, and there's no worry about endpoints for an odd, right? So if I had the limit of the cube root of 2x as x approaches, well, I guess I could use 32. Right? So no worries here on that one. The limit, I can just substitute in, right? So here, that's just going to be the cube root of 2 times 32. I was trying to make it a perfect cube. And so that would be the cube root of 6404. No problems plugging in. No problems plugging in if it's an even radical, so long as it's greater than 0. So if I have x approaches 5, the square root of 5x, that would be fine. I can use substitution. Right? So that would just be the square root of 5 times 5, which is the square root of 25, or 5. That's a 5 0. Right? But if it was as x approaches negative 5, well, now that's not what that would be valid, and I can't use direct substitution because that value doesn't exist for the square root function. So the limit of a composite function. This is kind of interesting. If f and g are limits such that the limit of g of x as x approaches c is equal to L. Right? So it means the limit of some function is equal to L, and the limit of f of x as x approaches L equals f of L, then the limit of f of g of x, and now we have a composite function as x approaches c, is equal to f of the limit of g of x as x approaches c, which equals f of L. So in other words, whatever this is, so whenever I get some value there, I can rewrite my limit statement, and so if x is approaching, so long as if I've got a composite function, so long as the value of the inside function is the same as the value the outside function is approaching, right? Then I can evaluate composite functions by taking finding the limit of the inside function and simply plugging that in to the outside function. we'll take a look at some examples in a moment, and I think that'll make that a lot clearer. And I think I'm at a point, even though the examples are coming up next, that I want to pause and move this to the next podcast, even though the next podcast is going to be kind of short. Yeah. So I'm going to go over this in the next podcast. See you in a moment. Bye for now.